questions about anything from last time? About anything? Well, today I'm going to talk about a useful tool in conformal mapping. It comes up all over the place, namely linear fractional transformations. And after you think about linear transformations, they're kind of the next level of complexity in the conformal mapping business. And they turn out to be very useful because they have properties about mapping lines and circles to lines and circles. So a linear fractional transformation is a mapping that's just a quotient of linear things. So AZ plus B over CZ plus D. And for it not to be a degenerate, weird thing, it could be a constant or not defined, for example, if C and D were 0. But in order for it not to be something silly, you need the determinant AD minus BC to be not 0. Otherwise, it's degenerate. So I guess the note about why we need that condition. If think of this matrix, A, B, C, D. If that determinant is equal to 0, that would imply that one row is a multiple of the other. The rows are linearly dependent. Okay, and let's see, the case where C and D are both equal to 0, that's a dumb case. Then the denominator of that thing would be 0, and it wouldn't make any sense, wouldn't be defined. So the case C equals 0, D equals 0, then the linear fractional transformation is not even defined. So that's kind of dumb. And if that's not the case, then one row being a multiple of the other would mean that that row would be a constant times the other. That means the function in the numerator or denominator would be a constant times the other one. So otherwise, that condition would imply that the linear fractional transformation is identically equal to constant. So that's just linear algebra. So that's why that condition is needed. I should emphasize or point out that the book calls linear fractional transformation, I call them LFTs, Möbius transformations. Not all books do that. And me, or I should say I, and many other books reserve the word Möbius transformation for special linear fractional transformations. So the Möbius LFTs are, they look like Z minus A over 1 minus A bar Z. Those turn out to be the one-to-one onto maps of the unit disk to itself. One-to-one onto conformal self maps. So they'd be analytic and they would map the unit disk one-to-one onto itself. And of course here A is in the unit disk. So A gets mapped to 0. That's nice to know. Okay, so I'll use my convention and call them these linear fractional transformations. Let's see, when you think about it, linear fractional transformations include these basic maps. So 1, z goes to r times z, where r is real. I call that a stretch. So all that does is stretch space by a factor of r. 2, z goes to e to the I theta times z. I call that a rotation, obvious, because the geometric feeling is that you just spin it around by an angle theta, the whole complex plane. That's a rotation. Number 3 is z goes to z plus b. That just moves everything by a complex number b, like vector addition. So b is a complex number. That's a translation. And there's one more basic map. Let's see, you can think of what would... Yeah. And it turns out that these are kind of all there are. They generate all possible linear fractional transformations. So, z goes to 1 over z. Let's see, that would happen when A, if you think about it, let me just think about this case. This is called inversion. This would happen if, let's see, A is equal to 0, B equals 1, C is equal to 1, and D is equal to 0. That gives you the inversion. Well, the reason we can understand these mappings so well is this a big fact. The basic maps 1 through 4 generate the LFTs. And I'll say what I mean by that in a second. It means I can build up one just by doing a sequence of those basic maps and composing them. Okay, so let's think about why that's the case. It's easy. The case C equals 0 would be kind of dumb. Let's suppose that the C equals 0 case is even easier. Let's do the C unequal to 0 case. So there's something in the denominator besides a constant. Then, remember my L of z is AZ plus B over CZ plus D. And we know how to do long division. And we need AD minus BC unequal to 0. Then if I do long division like you learned in junior high probably, let's see, to get rid of the AZ term, I would multiply that thing by A over C. That would give me AZ plus B minus AD over C. And when I subtract, I get, oops, I'm sorry, that's what goes, let me fix this. That's what's supposed to go here. Let's see, AZ, and this would be plus AD over C. And if you look at that BC, that's kind of the determinant. That's the remainder. That's the remainder when you do long division. And it's unequal to 0. Because you relate it. It's like minus, if you multiply that by C minus C, you get the determinant. And so what we see is that AZ plus B over CZ plus D is that quotient plus this number, B minus AD over C, divided by CZ plus D. Okay, that's after you do long division. And now it's really easy to see that the basic maps make that up. Let's see what I'm going to write C. I'll write that as R e to the I theta. And I have another number there. I'm going to write B minus AD over C. That's a complex number that's not equal to 0. I'll write that as capital R e to the I psi. Then if you look at this map, it goes to Z, goes to, let's see, think about how you would punch this number in your calculator. You'd start with CZ plus D in the denominator there, and then take it from there. So I take my Z in my calculator and multiply it by C, then add D, and I'll tell you the sequence. So first we multiply by C, so that's step 1 is stretch by R. And then we have times e to the I theta. So the next thing would be to rotate by theta. And then it's in the denominator, so I invert by 1 over z. Invert by 1 over z. And now I'm going to multiply by that complex number in the numerator. So next I stretch by capital R. And rotate by psi. Okay, I'm getting close now. The last thing I do is translate by ape over c. So I have to use all 4 kinds. Some I have to use twice. And so that's like 7 steps, 7 applications of those basic maps. Questions about that? Well, the interesting thing is that we understand those maps really well. Those are really elementary things. Let's see. Oh, the case c equals 0. Then my linear fractional transformation is AZ plus B over D. And of course that's A over D times Z plus B over D. And so that's just a map of the form AZ plus B. So that's a special kind of linear fractional transformation. And let's see, that it doesn't require any inversions. Only needs 1 through 3. no inversion to cook it up. So it's special. So let's think about the basic maps.
Professor?
Yeah.
So is the reason that we do in the one above, the reason we did the fractional division was just to get it so that there's only one z, because that's how the linear map would work. Like, we're trying to get it into a linear form, literally.
Yeah. So, yeah, the linear thing happens to be in the denominator, and that's why inversions are important. But everything else is one of the basic maps. Yeah. Let's think about what happens to the point at infinity. So here's an observation. The basic maps, 1 through 3, are the elementary ones. Let's see, what do? They map the complex plane one-to-one and onto itself. And they all satisfy the property that the limit as z goes to infinity, in the sense that we've been using for quite a while, the limit as z goes to infinity is infinity. And so we can think of the basic maps, they all map L infinity equal to infinity. So we're going to write that. We don't usually write stuff like that, but we're going to start writing stuff like that. Right? L of infinity equals infinity. So if you do that, if you define that like that, then basic maps 1 to 3 also map the extended complex plane one-to-one onto itself. So they're mappings of the Riemann sphere to itself, and they preserve the North Pole. Think about it like that. And now let's think about the basic map number 4. It's a zone inverse. So L of z is equal to 1 over z. And the inverse is itself. And we have the limit as z goes to 0 of 1 over z is infinite. And the limit as z goes to infinity of 1 over z is 0. So this linear fractional transformation, what is it? It would take c minus 0 one-to-one onto itself, and when I toss in the pointed infinity in, then it takes the extended complex plane one-to-one onto itself. So here I'm going to write L of 0 equals infinity, and this one's going to be L of infinity equals 0. Okay, so because of the 4 maps now, we have these properties that in all 4 cases, they map the extended complex plane one-to-one onto itself. We conclude LFTs map the complex plane to itself, the extended complex plane to itself, one-to-one and onto. Let's think about the cases. cases, the C equals 0 case, we just did that. Then the thing is AZ plus B. And that maps infinity to infinity. Okay. And let's do the case now. The rest of the cases are different. This is case C unequal to 0. Then let's think about what we've got here. I can write it as L of Z would be, let's think what happened. Let's think about AZ plus B over CZ plus D and take the limit as Z goes to infinity. This is kind of like you did in freshman calculus. Remember how you did that? You divided the top and the bottom by 1 over Z. You multiplied by 1 over Z. Then you got A plus B over Z over C plus D over Z. And when Z goes to infinity, those terms go to 0 in our quotients, and you get that this is A over C. So we're going to write L of infinity is A over C. And now let's think, and of course, as A goes to Z, yeah. And the other thing to notice is that L blows up when the denominator vanishes. And that happens when Z equals minus D over C. And so we'll write, let's see, we're going to write L of infinity equals A over C, and L of minus D over C equals the point at infinity. Okay, that's just our convention so that we can think of these as mappings on the extended complex plane, the Riemann sphere. Well, these things are a pretty interesting thing, and it's because the inverse of a linear fractional transformation is an LFT. So they actually form a group, a mathematical thing, called a group, like the Rubik's Cube. Let's figure out why that's the case. It's a pretty elementary calculation. If I write W equals AZ plus B over CZ plus D and do junior high school algebra to solve, I want to solve for Z in terms of W. So let's see, when I multiply through, I would get C times ZW plus DW equals AZ plus B. Now I collect all the Z terms and get Z times CW minus A equals minus DW plus B. So I collected all the Z terms and pulled them to one side and did that, and put all the other junk on the other side. And now I divide by that to isolate the Z, and to get Z is minus DW plus B over CW minus A. And I don't like, let's see, do I like that? What?
Never mind, I'm thinking of something else.
I think I don't like where my minus ones have appeared. So I'm going to multiply by minus 1 over minus 1. That's going to give me Z equals dW minus B over minus CW plus A. And that's kind of a interesting thing to stare at for a minute. Okay, so what did I get? I got the inverse of W is the Z, and it's equal to dW minus B over minus CW plus A. And of course that has the same determinant. So, same determinant. AD minus BC. That's nice to know. So it's an LFT also because that determinant is non-zero. And here's an observation that's going to make it easy to remember this formula. Remember, you must have seen this somewhere in your linear algebra studies, that the 2x2, the formal adjoint formula for the inverse of a 2x2 matrix is particularly simple. Remember what you do. You switch the diagonal entries and you put minuses in the other corners. And then you divide the whole thing by the determinant. And that's exactly what we're doing when we get the inverse. So the aha moment, when you look at this for a second, if we think of L as corresponding to a matrix, A, B, C, D, then the inverse of L corresponds to the inverse of that matrix. So you might wonder, well, why don't I have to worry about the determinant? Well, the determinant would multiply the numerator and the denominator by the same number, so it cancels out. So a thing to note, 1 over the determinant cancels out in L inverse because it's in the numerator and the denominator. So it's in the numerator and the denominator. So that's why we don't have to worry about that number. Of course, it's non-zero, so it's going to cancel out. That's interesting to know. And in fact, this thing turns out to be a group homomorphism. So here's another cool fact. Questions about anything? Yeah.
Can you explain what it means by cancels out the numerator and denominator?
Okay, that denominator, 1 over that denominator is a number. And so if I multiply it through the first row and the second row, and then make a linear fractional transformation out of that, that number would be on the numerator and the denominator, and it would cancel.
Oh.
So another cool thing is if I compose linear fractional transformations, let's see, L1, I'll write A1 times something plus B1. I'm not really going to do this. C1 times something plus D1, and this would be A2Z plus B2 over C2Z plus D2. I guess I have to write it again. Somebody did this once And once somebody did it, you never have to do it again. This turns out to be capital AZ plus capital B over capital CZ plus capital D, where A, B, C, D is what you get by doing matrix multiplication. I'll spare you writing it out and checking that. Oops, not plus. A2, B2, C2, D2. So, in fact, the map, so it's kind of a cool fact, a mathy kind of fact, the map that associates a linear fractional transformation with that matrix, A, B, C, D, is what's called a group homomorphism. So let's call that a matrix A. Is a group homomorphism from LFTs let's see, they map to 2 by 2 matrices with complex coefficients with non-zero determinant. 2 by 2 matrices with determinant non-zero, which is another, it's a group. You multiply those two together, you get one like that, and the inverse is one like that. Oh, by the way, let's see. I guess I should have mentioned this fact first. I've shown you what you need to see that the linear fractional transformations form a group in the mathematical sense. I showed you what the inverse exists, et cetera, et cetera. The only thing in the group, they form a group under composition. So the operation in the group is composition. And the group of 2 by 2 matrices, it's matrix multiplication is the operation. They form a group under composition. So I showed you what the inverse is. The only thing I haven't shown you is that the identity, of course, is the linear fractional transformation where you have 1 times z plus 0 over 0 times z plus 1. That's the identity map. Check. Okay, so that's the algebra facts. The next thing I want to think about are the geometric facts. And that's where they get interesting and fun. If you think about the basic maps, 1, 2, 3. Oh, so here's a geometric fact. LFTs map lines and circles to lines and circles. It turns out they can jumble them up. Interesting thing. The proof of that fact is very elementary. It's just kind of high school analytic geometry. So the basic maps 1, 2, 3 do that. That was just translation, rotation, and stretching. Let's think about them. In fact, the basic maps 1, 2, 3 do something even better. they map lines to lines. If you stretch a line, you get a line. If you rotate a line, you get a line, etc. Translating a line, you get a line. So lines get mapped to lines. Similarly, circles get mapped to circles. In fact, those mappings are called rigid motions. So it looks like maybe lines go to lines and circles to go to circles, but the map number 4 can jumble them up. So with the basic map number 4, which is 1 over z, can mix them up in all possible combinations. And let's see, I think I'll just give you this is, if you wanted to check it, you'd use just basic high school analytic geometry. But let me draw you the basic pictures. Let's see, let's take a line that goes through the origin. 1 over z maps that to a line that goes to the origin. It blows 0 out to infinity and sends infinity to 0, but it kind of turns it inside out. Let's see, thinking about conjugates, it would go like that. And of course, 1 over z is its own inverse, so the inverse of this picture would do that. So you note that 0 goes to infinity, and infinity goes to 0. So it turns them inside out, kind of. All right, that's one possibility. We've seen, remember when I was doing those horizontal lines when looking at the log function? So when 0 was down here, and I was looking at what I was taking the exponential e to the 1 over z. And I told you that those circles get mapped by 1 over z, maps those to circles that go like this. We've seen that before. That's an easy thing to do with high school analytic geometry. So that line gets mapped to that circle. And of course, the inverse is itself. So that circle gets mapped to that line. So that's a possibility. Then the last possibility is that you might have a circle. Let's see, I'll have a circle that contains the origin. What would happen? Those would get bigger. I think it would, my guess would be it would look like this. Different circle. It actually maps the inside of that circle to the outside of the other circle. It turns it inside out. So here a circle gets mapped to a circle. And if you think about what happens to the space, it takes the inside of that circle and blows it out to the outside of that circle. That would be easy to check if that was the unit circle. You'd believe that. Okay, so there's circles going to circles, and the last possibility is that if you have a circle that doesn't contain the origin, then it would map to a circle that doesn't contain the origin. Maybe this circle. I'm thinking of conjugates here when I do 1 over z. So this is another case where circles go to circles. And so it's kind of a tedious analytic geometry problem because you'd have to think about all these cases. But it's very elementary. So how would you the proof? High school analytic geometry. Or maybe it's college analytic geometry, I don't know. They never ask you to do this in high school. And luckily, I'm not going to ask you to do it in college either. So it's kind of a routine thing, but it's not fun. Well, here's a fascinating thing. So I've established that fact. Since we know it for the basic maps, it's true for all LFTs. Here's a fascinating picture. On the Riemann sphere, lines and circles are all the same thing. So let me draw the Riemann sphere. Remember that we put a sphere on top of the complex plane. So this is the complex plane. My Riemann sphere, I like to put the south pole on the at the origin. And then the point at infinity corresponds to the North Pole here. A line, if I draw a line in the complex plane, it corresponds, if you think about stereographic projection, it would correspond to a slice. You'd slice the sphere there. And so this is a line. This is a slice. And if I draw a circle in the complex plane, it also corresponds to a slice. So if I have a circle over here and do stereographic projection, it would correspond to a slice over here. So we have a circle. This one would correspond to a slice. Take a knife and slice off a piece of the sphere. So, unless if you think, excuse me, if you think about lines going through the origin, those would be longitudinal lines through the point at infinity. So those are also slices. That's slicing the thing in half. So lines and circles in C correspond to slices. That's fascinating. Kind of means you ought to be doing, when you think about linear fractional transformations, you ought to move into this Riemann sphere to do it. There's lots of beautiful simulations, pictures of what happens when you do that, if you Google it. Well, lines and circles are interesting because they're determined by 3 points. So, a big fact for making linear fractional transformations useful is that an LFT that fixes 3 points is constant. That's not constant, is the identity. The only way you can fix 3 points is if you have the identity. Think about that. If I had, let's say I have L of Zj is itself for 3 different points. That would mean that Zj is AZj plus B over CZj plus D. when you try to solve for the ZJs now, you realize it's a quadratic equation. C times ZJ squared plus A minus D ZJ minus B is equal to 0. So I'm doing the case C unequal to 0 here. The C equals 0 case is even easier. And so I'm thinking that now, I've got a quadratic equation that has 3 roots. Quadratic equations have 2 roots. How can I have a quadratic equation that has 3 roots? There's only one way, and that is each one of those things has to be 0. So it must be so 3 roots. It can only happen if C is equal to 0, A minus D is equal to 0, and B equals 0. Okay, let's say, so C is equal to 0, and so the determinant would be A D minus BC is unequal to 0. And here I have B and C are both 0. So A times D is unequal to 0. That means neither one of them are 0. And D is unequal to 0. And now this last equation says that A equals D. And so my linear fractional transformation is C is 0, 0 times Z plus, what? No, A times Z, B is 0, plus 0 over C is 0, so 0 times Z plus D, and A and D are equal. And so this is just Z. So sure enough, the linear fractional transformation has to be the identity. And the C equals 0 case is even easier. Easier. Because then your linear fractional transformation is just AZ plus B. And you'd have a linear thing with 3 roots. Let's see. Kind of running out of time today. Well, an exciting consequence. Let's see, a corollary is if 2 linear fractional transformations agree at 3 points, if L1 equals L2 at 3 points that are different, implies L1 is equal to L2. And an exciting fact that makes 3 special is 3 points determine lines and circles. So fact, 3 points determine a circle. 3 points in C determine a circle uniquely. And 2 points plus the point at infinity determine a line. So let's see, 2 points.